right, welcome everyone. So today's going to pick up where we left off last time, and then later today the homework for the hearing section is going to be posted, and we have a demo that's going to go through a part of that homework that is related to cochlear implants. And that exercise is going to really closely mirror what you guys are reading about and thinking about for your PBL3 assignment. All right, so last time we finished up by saying that there's two kinds of hair cells in the ear. So inside the cochlea, we have outer hair cells and inner hair cells. And the inner hair cells are the ones responsible for perceiving sound, and the outer hair cells are the ones that tune and amplify the sound in order to help the inner hearing cells function. And one of the key things there is that if your hearing's damaged, for instance, by overexposure to very loud noises, in most cases, it's the outer hair cells that are damaged. And if your hearing is completely lost in that, or if those outer hair cells are pretty much completely damaged, you'll have an effective reduction in your hearing of about 40 decibels, which is pretty intense. So I mentioned this a few times, but the functions for the intensity of the sound wave are measured in decibels by comparing the intensity to a reference. And that reference is what's the threshold where we can just barely hear. So there's two kinds of ways to talk about intensity. One is the hearing sound level. And what that is that compares just the actual physical intensity of the sound to a reference value. And it's applied in a logarithm function to help sort of keep the numbers in a manageable sense. And what it does is it takes the logarithm, the intensity of the sound, divided by that reference, that very minimum sound where you can just barely hear. It has units of decibels. And it turns out that reference sound for most people is somewhere around 10 to the negative 12. And here's where the physics comes in. It's watts per meter squared. So we said that all waves transmit energy through a medium. And you can actually measure the amount of energy being transmitted through sound. And if you do, you would find that if you were able to transmit 10 to the negative 12 watts, so that's milli, micro, nano, is that down to the pico, I think, the picowatt level per meter squared. That's when you just barely start to hear. And I think I've said this maybe not quite correctly a couple times, so pay attention to right now. Let's see what this logarithm does to how these decibels work. So let's say that our sound comes in around, let's say 10 to the negative 9 watts per meter squared. So down in the nanowatts area. So how many times bigger than the reference is that? 1,000? Yeah. So if we apply the formula above, what we'll end up with, the hearing sound level is 10 times the log, and this is the log base 10, as opposed to the natural logarithm. So if you're going and doing something like this in MATLAB, you just want to make sure you have the right logarithm. And then, so we got 10 to the negative 9 divided by 10 to the negative 12, which is 1,000. And the total thing ends up being 10. What's the log of 1,000? Yeah, 3. So 10 times 3 is 30. So let's say that instead of 30 decibels, let's say we have a sound that's 50 decibels. So try to figure out how much more intense is this sound than the one we just looked at. So we know it's 10, the logarithm, the denominator stays the same, but now we have to figure out what the numerator is. So any ideas for that, what it might be? Yeah, that's great. So we know we need to have 10 times 5, and which is basically 10 to the 5th, and 10 to the 5th bigger than that is 10 to the negative 7. So that means an increase in 20 decibels corresponds to intensity of, how many times larger is that? So it's 100 times larger. So if that decibel was, let's say we did an increase of 40 decibels, so that would be from 30 up to 70. How many times larger is that? Yeah, perfect. So it's like the one I'm most familiar with is the Richter scale with earthquakes, where a linear increase ends up going into the power of 10 to that power. So you get really, really large increases in intensity with relatively small increases in decibels. But to our ears, a sound of 50 decibels might sound as far away from 30 as 70 is from it. So when it comes to human hearing, it actually turns out that we need this sort of exponential increase in power to perceive what sounds like a linear increase in power. It's not exactly that. Well, we'll get into a little more detail of that next time, but it's a little bit transformed in that sense. So we have loudness. So that's sort of, we have two vocab words here. Hearing sound level is more the precise, there's a physical way to measure that. Loudness is more the subjective measure of sound intensity. So it's how loud is it perceived would be sort of how you talk about that. And then as a complement to the hearing sound level, I should mention that there's one, the pressure sound level. And instead of talking about intensity, it's going to say we have how much energy or how much intensity is in our sound. Now we can relate the difference in pressure of those sound waves, and I'll draw a figure of that in just a sec. We're now comparing sort of an increase in pressure of our sound to an increase in pressure for a reference. And we take the log of it, but this time we multiply it by 20. And so that's just a matter of, if you take a look at a sound wave, so let's draw a little sketch of one. So there's what the air actually looks like. The shaded areas are compressed parts of sound. The more spread out areas are expanded, lower pressure parts of the air. And if we were to plot pressure as a function of time, remember that we get something like that. It's a little askew, but that's just sort of imagine that the shaded parts line up with the tops of that curve. So if we measure how tall that wave is, that's our delta pressure. If we wanted to talk about how much energy is in that, that would be the square, it's related to the square of the pressure difference, which explains why we have a 10 times the logarithm when we're talking about energy, but a 20 times the logarithm when we're talking about pressure difference, because one has a square in it. So if you, I know some amplifiers, some stereos will output the sound level in decibels, and in a lot of scientific contexts, if you're going to do experiments in hearing, you're going to use decibels, so it's good to have a sense of where those come from. All right, so now that we've got that, let's go back to talking about the cochlea and how the different hair cells and also the sort of the thickness and the stiffness of the basilar membrane affect frequency perception and frequency discrimination. So back to our schematic diagram of the cochlea. If we unwrap this organ, which normally is sort of spiraled in on itself about 2.5 times, but if somehow we could unwrap it so that we have the oval window on one side, the round window on the other, and remember that the middle ear bones, the last one of them, the stapes, is connected to that oval window, and that's where the sound wave enters the cochlea. Now this membrane in the middle, the basilar membrane, changes both its width, or its size, I guess thickness probably, and its stiffness from one side to the other. So on the oval window side, we call this the basal side, and we call this the apical side. So the apex versus the basal. On the basal side, it's sort of very narrow, so it has a low mass per unit length, and it has a high stiffness. And on the other side, remember we said it's wider, so it has a high mass per unit length and a low stiffness. And then we solved that the natural frequency of a mass spring system is equal to the square root of its, let's see, did I do that back? No, that's right. It's equal to its stiffness divided by its mass square root. And so here we have a very high stiffness, low mass, so we get a really large frequency, which ends up for human hearing to be about 20,000. And on the other side, a very low one, about 20 hertz. So this is stuff we've all seen before, but it's important to really have this down, as everything afterwards is sort of built from here. And so what that means is that if we put a sound wave into the cochlea, so let's say we have sort of this, it's not the fastest wave, it's not the highest frequency, it's also not the lowest frequency, it's somewhere in the middle. Let's say maybe 2,000 hertz. Oh, forget it, let's say 1,000 hertz. So what that's going to end up doing is creating a bit of a standing wave somewhere in the middle of the cochlea. So there's going to be a rapid and large amplitude movement of the basilar membrane there. And what that movement's going to do is create it's going to cause, I guess, a stretching and a contracting of the hair cells. Because remember, from the diagram you have yesterday, from the picture in the very first lecture, the stereocilia of that hair cell, sort of the hair-like part of it, are connected to one membrane on the bottom and one membrane to the top. And when we start to get movement, it's going to cause those hair cells to move, left to right in that figure. In one direction, they cause a lot of action potentials to fire, and the other, they cause not very many. And that gives enough of a signal for the brain to detect there's a lot of movement at this part of the cochlea. So, what's the, I guess, how much basilar membrane movement, which is going to be how much inner hair cell movement, do we have at a particular part of the cochlea? And just to answer that question, we would have to say, well, let's take this part of it, and let's find what its natural frequency is. So somewhere, right in the middle, we might theoretically have a frequency that perfectly matches the input wave. But on either side of it, we'll get some peak displacement there. But on either side of it, we're still going to get some displacement. So if this is, last time we used X naught to say how much displacement's happening, sort of the peak value of a sine wave. So depending on the, I guess in this sense, it's both the frequency or sort of this distance. Let's call this distance, well, we already used X, so let's call it just sort of the length down the cochlea. So we could say this x-axis is frequency, or we could say how far down the cochlea are you? And there's sort of a wide area that's going to be stimulated. And it turns out that for a given part of the cochlea, without any outer hair cell movement, even a pure tone, so exactly 1,000 hertz sine wave, is going to stimulate a pretty wide part. And it's going to sort of, if that was all you had, it's going to come to the brain and not give you the most frequency discrimination possible. So that's where we need the outer hair cells to come in. So let's take a moment to just log what we saw there. So let's expand that graph I drew. Yes? So that's the length down the cochlea that we're looking at. So let's say this whole thing is, maybe this whole thing is, big L. We could use little l to say how far down, what sort of fraction of that big L are we? Okay, so let's say that now, we're not talking about a width of the cochlea. Let's just say that we're exactly at one point. So this is for a single inner hair cell. Now let's say that inner hair cell is right here. So we know that and its natural frequency is 2 pi times 1,000 hertz. So that's saying 2 pi, 6,000 something radians per second, or 1,000 periods per second. So for this one, a 1,000 hertz, if this is, let's say, this is 2 pi times 1,000, that's where it's most sensitive. So if the y-axis is sort of what's this, or displacement, then I'll use an x naught, comma, BL for the basilar membrane. This is where the maximum amount of basilar membrane displacement happens, the maximum stimulation going to the hair cell. And then as the frequency goes up or down, what's going to happen to that intensity? Yeah, it's going to drop off. And it's not going to drop off as quickly as we might hope. And so what that says is that, if we have a 1,000 hertz sine wave, sure, we're going to get some activation. We're going to get quite a bit. But let's say we go up to 2,000. Let's drop the 2 pi notation. This is converted to hertz. At 2,000, let's just make it a little more dramatic. At 2,000, we're still going to get some activation. So still some activation. And also, if we go down to 500, we're getting a good amount too. And so if we're listening to music where, between 5,000 or 500 and 2,000 hertz, that's 2 full octaves of range. So we need way more sensitivity than that if we're going to enjoy listening to sound. And so what needs to happen is we need to have some way of tightening this curve, making it more extreme. And that's where the outer hair cells come in. So what those outer hair cells are going to do is, well, first of all, let's say, so we have waves coming down the cochlea, and they're sort of, they're running into different parts of it, and then they're sort of stimulating the basilar membrane a lot there. So if, for instance, we put a really high frequency wave in there, it's going to cause the biggest deformation much, much closer to the oval window. And what's actually going to happen is, for higher frequency signals, a lot of their energy is going to be absorbed by the membrane before they go very far. So we said that, if just left to its own means, the basilar membrane would have that sort of movement curve as a function of frequency. But because the high frequencies, the stuff over here on the right, has to pass through, its sensitive part of the cochlea before it even gets to where we have a graph here, not as much of its energy is going to arrive. So there's actually going to be a drop-off in the intensity curve there, because in order for the energy to get there, it has to pass through the part of the membrane that's sucking a lot of the energy out and putting that into higher frequency detection. So that narrows it a tiny, tiny bit, but it's not quite good enough. So what we need to do is get a situation where we're actually going to amplify and narrow and really tighten up this curve, and that's exactly what outer hair cells do. So it turns out the way that an outer hair cell behaves is, let's say, if we wanted to look sort of in a more mechanistic or descriptive of the behavior, maybe a little bit less of how we get this done. We said that the basilar membrane is kind of like a mass on the end of a spring, in which case it would behave exactly like we predicted. But kind of like with the Hill model, we can usually add some complexity to our model if we add a damper in there. Most physical systems don't act entirely like a spring and a mass. But so what a damper does is, it just makes it harder to move fast. It turns out though that the outer hair cells are able to create what effectively is a reverse damper. So remember, a damper is the faster you move, the harder it is to go that fast. If you were to make B negative, so that would be negative damping, the faster you move, the more it's going to move you. So you give it a little bit of start, and it's going to just go crazy. It's kind of like remember the divergent force field from the muscle lecture, where you're reaching through a line, but when the force field's turned on, you deviate just a little bit, and it pushes you off course. So what's happening here is if the basilar membrane starts moving a little bit, the outer hair cell is going to give it a huge push up and down, and the amplitude is going to be dramatically increased. And that's not really frequency dependent. As soon as part of the membrane picks up some energy, it's going to go crazy. And it turns out that if you look at these sound sensitivity curves, what you end up seeing is that they have a really strong peak, sort of at the very highest frequency that hair cell is sensitive to. So as soon as it gets a little bit of movement, so remember, let's label a few of the points here. So we saw that there's a decrease here. Let's give that a 1. So there's a decrease sensitivity at high frequencies, because that energy is absorbed earlier in the cochlea. So that energy doesn't even reach this part of the cochlea. It doesn't even reach this hair cell. So it's absorbed by the more basal, so the ones closer to the base of the membrane, closer to the oval window. So that's high frequency part of the cochlea. Okay, so that's one effect. The second effect is sort of this huge increase right here, and that's sort of a negative damping effect. And that's caused by amplification of the vibration by the outer hair cells. And what's going to happen later is that if we went, so this is the hair cell responsible for 1,000 hertz. If we went even deeper into the cochlea, so if we went further down here, so this is, the frequency is going down as we go in that direction. For the hair cells down there, they're going to lose even more. So they're going to lose even more of the energy in the parts above it, because now that energy is being consumed, and the outer hair cells are sort of capitalizing on that. And that part of the membrane before it is being activated even more by that wave. So we get this effect where you sort of have a smooth increase, then a really intense spike in sensitivity, and then a pretty sharp decrease. So let's draw those sensitivity curves for a couple different hair cells. So I could take a question or two now, but it might become a little more clear when we draw those sensitivity curves. Okay, so I'm going to do a little bit of a flip from up to down. Yeah?
Does that word say like underneath negative damping?
Oh, sorry about that. Negative damping effect caused by amplification of, oh, that is bad. That's vibration by outer hair cells. Okay, so x-axis, that's going to be frequency again. And we're going to talk about in hertz, because that's what a lot of us as engineers are probably more used to that. And then the y-axis now is going to be the threshold intensity in decibels. Yeah, just the threshold intensity in decibels, at which that's when a particular hair cell is going to be stimulated enough to actually detect if there's some sound going on. Let's draw more or less the hair cell we just looked at, and let's give it a 0 decibel line here. So this line represents 0 decibels. So that's at 0 decibels, that's where the sound is actually equal to the reference. So the hair cell above sort of has some drop and then a really strong peak value, and then deteriorated. So if you can sort of see both of those on the same time. It's really just flipped upside down. And what that means is that because the hair cell is most sensitive at that peak frequency, so let's say that's our 1,000 hertz from above, because it's most sensitive there, because it amplifies the sound the most there, it requires the least amount of sound to get the thing going. So that's that amount of sound that just barely is perceptible, that 0 decibel point, that's going to occur when the hair cell is absolutely the most sensitive. So that's one hair cell. That's the one that's peak is at 1,000. So let's get a few more on there. So usually if we have lower frequency ones, they have sort of a tighter curve and then sort of a less dramatic effect. We get a little higher, it's widening out. You kind of see that intense amplification spike. You go even higher, and actually sometimes the sensitivity curve comes back up, and then it spikes even further up. And what you see here is that the frequency at which these hair cells is most sensitive is actually changing because of the outer hair cells. So for instance, let's change color. If we just look at this most high frequency hair cell, if you just looked at the sensitivity of the decibel number in there, you would find that it, more or less, it looks something like that, where it has some peak value right around here. Above that and below that, the sensitivity drops off. But because the outer hair cells are going to, respond in an almost explosive way to any amount of movement, as soon as that high frequency stuff comes in, the sensitivity of that hair cell is just going to get out just really, really big. And so that if you look at that, so we'll call this point 3. So outer hair cell sort of response can actually increase the frequency at which the inner hair cell is most sensitive. And what you end up with there is these really high frequency hair cells. What's going to happen then if someone has hearing loss? If they're sort of the inner hair cells for the highest frequency, if the outer hair cells for those are damaged, what are really high pitched sounds going to sound like to that person? So there's going to be 2 effects. So how about the intensity of that sound as those outer hair cells get damaged? Sorry, say it a little louder. Yeah, so the amplitude is going to get tiny. They'll barely be able to hear. They'll need a much louder sound in order to hear something going on. The second one, I'll just give it to you, is that the frequency is going to shift down. Those outer hair cells get damaged. That means you lose that really big spike on the end. And you go from maybe 20,000 hertz is very, let's say this is just a 15 kilohertz hair cell. It's going to go from having a peak sensitivity of 15 kilohertz down to having a peak sensitivity of maybe 1,000 or 1,500. And so there's a distortion in what things sound like as damage occurs. So, and then one more point for this curve is, do you see any place on that graph where a pure sine wave, all at one frequency, is going to activate multiple hair cells? So remember that, if we have a sound that's, so let's see, this is our example sound. So it's at maybe 900 hertz. Its intensity, let's say, is 20 decibels. So that's going to be the threshold for detection by that one hair cell. It's not going to be as intense as if it's at the peak value, but based on the 4 that we're looking at here, only that one hair cell is going to be activated. But what happens if we increase the intensity of that sound to be up here? So this is, let's say, 80 decibels. How many hair cells look like they're going to be activated then? Did we cross any other thresholds? Which one? Yeah, so we've crossed now the high frequency one. And so what that might do is, if you sort of bring the higher frequency one, you might get a little bit of like a ringing sound in response to a lower frequency stimulus. If that stimulus is really strong, and that's because you definitely are picking up that frequency with the hair cells most responsible for it, but you're also picking up hair cells responsible for a higher frequency, and those will probably assume that a higher frequency really exists. And I think based on that, I might have misspoke a little bit about damage to the ear, lowering what high frequency sounds sound like. I think it just means that you're not detecting those high frequency sounds. So sorry about that. Okay. So this graph will come up in the homework, but so if you have any questions about that, now'd be a great time to ask. Yes?
Remind me what each of these different curves represent.
Okay.
Trying to represent like different groups of hair cells.
Yeah, so this, well, usually they're measured, so let's see. Let's just do this graph generated. They're usually generated by measuring the neurons connected to the inner hair cells. So each of these lines, of course, it sort of represents one hair cell's sensitivity curve, but it's generated by measuring sort of the activities of the neurons connected to those cells. Connected to inner hair cells. And so here, this might be, let's call this inner hair cell 1, inner hair cell 2, 3, and here we got 4. And so in actuality, there's about 3,000 of those curves, and they sort of start on one side and get progressively to the left, and we've just taken 4 of them and plotted them. Any other questions right now? Yes? Okay, so let's say we were playing a very high frequency sound over 15,000 kilohertz. If our hearing's damaged, that's going to remove that large spike on the right. And so we actually won't hear really high frequency sounds until their intensity gets above the curve drawn without the spike. So until we cross that blue line. So we need probably 80 decibels instead of 1 or 2 decibels to start hearing that frequency. Okay, so we've seen that. Let's answer one more. Yeah.
So basically, you guys where ear gets damaged, like the right side of the graph.
You get rid of those bigger spikes. So if we take a look at one more of these, let's head for the lowest one. It's sort of its behavior without outer hair cells is probably, so let's do a key. This is sort of the inactive outer hair cells. And this is with active outer hair cells. So that dashed line is probably what the sensitivity would look like without. And for this one, adding the outer hair cells doesn't really change the frequency associated with that neuron as much, but it does, dramatically narrow its sensitivity curve. And so we see here that the outer hair cells allow us to have a much better frequency resolution, discern pitches that are much closer to each other. But it apparently isn't quite good enough because the brain has one more trick up its sleeve to do this. So there's an alternative method of frequency discrimination. And and that is phase locking. So what phase locking says is that it's not only about which inner hair cells are being activated. The brain actually has a way to detect how quickly the action potentials from that hair cell are coming in. And why that actually helps us is that the action potentials tend to fire at about the same point on a sound wave every cycle. So if we draw, let's say we draw the pressure of a sound wave, which would really correspond to the display in time. That would really correspond to the displacement of the basilar membrane, the stretching of the cilia at the end of the hair cell. It turns out that if we were to look at how the action potentials are firing here, so these are the neuron action potentials, they actually sort of fire at the same point every one of those periods. And especially for really high frequency stuff, this can become helpful. And if we go to really high frequency, it turns out we can get fast enough where an action potential can't even fire every one of those periods. Maybe it fires on this one, fires again on this one. Let's say it gets a real quick one, fires again there. So it's missing some of them, but the information is still there to some extent, and that's because the difference between these action potentials is always going to be an integer multiple of the period. So let's say this one's got period 1. Over here, so this is, draw the periods on both. So let's say this is the period of the higher frequency, T2. This one is 1, 2, this is 3 times T2. This one is 2 times T2. The key is that it's always spaced out by an integer of the period of that sound wave. And so if you hear a high frequency sound for a second, maybe it's a 10,000 hertz sound for that full second, you've had 10,000 periods and maybe you fire every 12 or 13 of them. You have 100 chances per second, or maybe, no, about 1,000 chances per second. That's too fast, so it must fire every 50 or so. Let's say you have like 100, 200 chances per second to count how many periods could possibly be between those successive peaks. And so it doesn't give you an exact measure of frequency, but let's say these sound waves are coming in at about 100 hertz. We know that let's say if there's 10 periods in 100 hertz, so 100 hertz. Oh, I'm making myself in trouble here. It takes an action potential about 10 milliseconds to fire. So let's say an action potential fires every 20 milliseconds. So what that could mean is that the period is 20 milliseconds. It could also mean that the period is half of that. Or it could be really any multiple of that. So it could be, we could have 3 full periods, in which case it's about 6.7 milliseconds. So, you get a couple choices. I think this would correspond to 50 hertz, 100 hertz. Gosh, I hope I'm not wrong with that, but that's 50 hertz. There's a couple possibilities for what frequency that sound wave could be, just knowing how fast the action potentials are firing. So how do you think the brain would pick which one of those it is? Well, let's say we don't know. What other information does the brain have? I think maybe over here. Yeah, so the frequency localization of the hair cell that it's talking about. So let's draw sort of the whole schematic. So we have a cochlea. Let's say it has a bunch of different hair cells along it. Each of those hair cells is connected to a neuron. Those neurons are sort of bundled together into the auditory nerve, which sort of goes, and it goes, sort of travels not very far, just from the ear to the auditory cortex in the brain, which has, some folded brain-like shape to it. And then those neurons come out of this, nerve, and they actually go and they stimulate different parts of the auditory cortex. This is the brain's auditory cortex. And just like this, frequency is corresponding to length along there, so it's a tonotopic mapping. Here, there's also a tonotopic mapping there, where different parts of the cortex correspond to different frequencies. So we could say, on the very right side of the screen there, I know my sound waves either 50, 100, or 150 hertz. But I know that sound wave may be being detected right here. So let's magnifying glass that. So we know that wave maybe corresponds to 100 hertz. That's where that inner hair cell is most sensitive. So if it's getting 100, 50, and 150, it's probably the 100 one. And what this is going to tell us is that, it's not the hair cell for 103 hertz, it's not the one for 97, it really is the one at 100. And those two things together give us very good precision. And it turns out that human hearing, so hearing, is sensitive to about 2 to 3 hertz differences. So we can actually hear pretty small changes in frequency. But below that, we have to do different tricks. In music, if two instruments are playing together, they have to listen for interference patterns between two waves that are very close frequencies because the brain stops being able to detect. But to go from what we had, where we estimated maybe at 200 hertz, if there were no outer hair cells, down to maybe 10 or 40 if there were outer hair cells but no phase locking, down to this 2 to 3 hertz with all those things combined. That's where that really good performance comes in. So that's the working ear. So now we have to go and talk about how do we help a non-functioning ear hear again. And that's where the cochlear implants that you're learning about in the PBL come in. And during the TA lecture for that, we'll go into a little bit of detail, a good amount of detail about how those work. I'll give you a little more next time. But I wanted to give a demo just to give you sort of a listening idea of what the end goal is here. Other side. Okay, so in the homework, you're going to be using this pretty neat tool here. The font's a little small, but it's a cochlear implant simulator. And so what you can do is, it's got some voice things that, if the speakers work, we can listen to.
25.
Oh dear. That will not be sustainable. Okay, let's try this.
25.
That's a little better. Okay, so what's it sound like from a cochlear implant? How'd that sound? And so in this simulator, a few things that homework will walk through. First of all, these sounds, it's not like you can stick it into someone's brain and measure exactly what they're hearing. It's sort of using a little bit of engineering intuition to guess what it should sound like. And this is playing more of I guess, it's playing what we expect it might sound like. I've heard two guesses, either that really fuzzy one or the sort of ringy metal one. The truth is somewhere probably between those. So what we're going to do in the exercise is this thing's got a couple, you can actually input a music into it, so let's do that. So, in honor of protesting injustice, let's do this one. All right, let's see if we can. So, do you think you might want to listen to that? Someone help someone out. Because I think there's probably some people who can use their hearing restored here. Okay. So, the goal of the PBL is going to be how do you restore good musical hearing? And the problem with these standard cochlear implants is the frequencies. So you're basically breaking all the information in sound, which is this broad spectrum between 20 and 20,000 hertz, and you're breaking it into a bunch of discrete chunks. So maybe between 200 and 400 hertz is one chunk, between 1,000 and 2,000 hertz is one chunk, and you're just saying how much of that really intricate information just between that huge chunk of data is there, and we're just going to give it one number, and we're just going to stimulate that wide frequency at that amount of intensity. The problem is in music, you don't just have 1,000 to 2,000. You have like 440 hertz is one note. You go up to maybe just 490. You're hitting another note. You need to have much better discrimination. So what we can do with cochlear implants, though, theoretically, is maybe we're not going to get the amount of discrimination the human ear has, but maybe we could at least hit the frequencies that we're looking for. And so this song, I believe it's in the key of A minor, and the homework will walk you through how to do this. So if we were to input a cochlear implant that selectively identified the notes associated with an A minor scale. Oh, that's not quite going to do it. There's 18 channels. And then we need to tell it to use our files. Then we'll start the simulation. That's going pretty fast. That's good. Okay, let's see. How does that compare? It's still not good, but I think I'm not the most musically, my ears aren't the best musically, but what that has to it is at least the different combination of pitches we're getting are more resembling those minor chords present in the song than they are with the really uninformed one. And so for the exercise for the homework, which I'll get it up this evening, you're going to just take a song that you like. You can record it on your phone if you don't have the digital version of it or something. And you'll sort of be going through an exercise to say, how can I tune a cochlear implant that would make this work? For the PBL, though, you have to answer the question, how can I actually make this work for a person? Like this is now their primary source of hearing. And sure, they might have a favorite song they want to listen to with it. But you're going to have to answer the more complicated questions of how can you make this thing versatile enough that it can be used in everyday speech, but also used for music, and then music also has different keys, different styles, different frequencies, some is high, some is low. If you wanted to look at the whole range of music someone might want to listen to, you might have on the order of 100 different notes, and that's probably unfeasible. So start to think about how you can answer questions towards taking that sort of unfeasible goal and bringing it into something a little more practical. That's where you can start thinking about for the PBL, especially giving you some of this insight on the homework exercise. All right, well, I'm over time, but are there a few questions we want to pack up?